Okay, hi everyone. This is the official start of this webinar. We are very excited having you among us. We expect quite some people, close to 100 people today, all over the world, quite international audience and from different backgrounds. But we all have one thing in common. It is water. So we all relate to the water industry in one or the other way. And this is what we are going to talk about today. And specifically how CFD can be helpful in the water industry. So CFD is Computational Fluid Dynamics. We will introduce it, we will talk about it, we will give you a lot of examples on what CFD is. But specifically, we will also be talking about the needs of different stakeholders. So in the water industry, there are different stakeholders. We will be touching upon them, and they have slightly different needs, and they can slightly differently benefit from CFD. Of course, what is also very important is that we show you the latest case examples. This is, of course, very valuable to inspire you with what is actually possible today. So this is a live webinar. This is no fake. It's a real stuff. So we can actually interact live today. So what are the today's objectives and content? Just to put the expectations right. What is the objective? Well, by the end of this 1 hour webinar, you know how CFD can be helpful for your case. This is actually the why. Why should you be doing, or how can you actually benefit from CFD, and who? So this means depending on the target audience you belong to, the target group, you might have different benefits. You can also make best use of it in your specific situation, because maybe you're in a design stage, maybe you want to optimize something, you're scaling up a process, it is very different. So these things are points we will be addressing in this webinar. The target audience is actually non-CFD experts. So we know we have a couple of real diehard CFD fans here. Well, just get inspired by the applications, but for really the details on the models, more details on the cases, I would really recommend you to contact us or go to our website and read our blogs, okay? So this is all about the applications, and we will not really scare people away here with formula. What is the content? Well, we will discuss the needs of different stakeholders, some common misconceptions and must-knows about CFD. We interact daily with the industry. We are running a huge amount of CFD projects at the international scale, and we see quite some patterns. And we thought it was very important to bring forward these patterns and also address some of these big misconceptions. Of course, this is the most fun part of this webinar. My colleague, I will introduce him within a minute. He will be showing practical case examples. We will try to inspire you with a lot of examples. Avoid going deep, but we will go wide and show you a lot of different cases. The format is slides. So this is the slideshow. We will have a couple of presenters and one moderator. We will have live Q&A. So this means if you hover over your screen right now, you see a Q&A button. This is questions and answers. So if you use that window, you can answer our questions. You can ask our questions, and we will be answering them either in written form, or if they are relevant for the broad audience, we will answer them live. So please don't hold back, use the Q&A as much as you can. And then we will have a short questionnaire after the webinar. We are always interested in hearing about the next interesting topics to talk about, but also your feedback to improve our webinars. That's the content of this webinar. A lot of dense content, but of course we have to make use of this 1 hour as efficient as we can. Who are we? This is AM team. This is our current team. A lot of nice people to work with, I must say. Our company is located in Ghent, headquartered in Ghent, but we have customers all over the globe. And also our team is quite international. So these people are actually from 4 different continents. It's a mixture of chemical engineers, environmental engineers, mechanical engineers, many engineers, and lots of people are exclusively focused on CFD modeling as their full-time jobs. Who are the presenters? of today. This is myself. I'm Wim Oudenaert. I'm CEO and co-founder at AM Team. And I have a background back then when I was doing my PhD on process modeling, physical, biological process modeling. Then we have my fellow co-founder, actually, Ousmane Rehman. He's the CTO, and he's now on the screen for a while. He's the CTO at the AM Team. Ousmane has, really an experience in CFD where I'm a bit jealous of. I could never achieve that. He has really modeled so many installations and has a vast experience with a lot of CFD models. Then we have Celia de Wilde. Celia is actually business development manager at AM Team, working with a lot of customers all over the globe in the water industry, both at drinking water side and the wastewater side. And then we also have Willem. Willem is our marketing communications manager. He's also saying hello now. He joined our team 1 month ago. So it's really cool to have Willem on board as well. What we always put on a slide is our customer ratings. Well, we are a simulation company. We are not doing anything else. And if you are a simulation company, the only way to actually last is to offer practical solutions to the market. That is the only thing that matters, and that is important. The market decides on the value you provide. And we like to put them on the slide. They are quite good because simulation is something abstract. It is like not perceived as reality. It's on a computer. And the only way we can prove actually that we offer a lot of practical value to the market is by showing these ratings of a lot of customers. So as I said, we are headquartered in Belgium, and our company is providing cutting-edge process simulation services to the global water industry. Recently, we have also launched a process industry business unit. But it's very interesting because these needs and problems across industries are very, very similar. You will probably know a lot of these logos that are on this slide. If you're working in the water industry, it's unavoidable. It's actually a mixture of 3 categories of customers. We have the end users, which are drinking water utilities, big industries with big wastewater treatment plants, or we have consulting and engineering firms. A couple of are on this slide as well. And then we have technology developers and vendors developing and bringing to the market new technologies. These 3 are our customers, and we are very unique actually by our combination of cutting-edge simulation capabilities with process understanding in the water industry. So our customers are all over the globe. This is what I mentioned already. Nowadays, in these digital eras, it's very easy to actually work remotely. Okay, let's enter the content here. CFD easily explained. These are some basics that are really fundamental for you to get everything we will be touching upon in this webinar. We have to start with the basics. You should have a basic understanding of what CFD is. CFD, Computational Fluid Dynamics, is actually a physics tool by heart. So the core is really physics equations. We will not put them on the slide here. They are quite sophisticated, but luckily there's very good software to solve these equations. It's not a trial and error process. What do we mean with that is it's a physics model that is really by nature quite accurate if you apply it properly. And then you can structurally apply it to actually get to your goal. One example on this slide is an existing system. At the left, this is a wastewater treatment plant. It can be any system, drinking water, storage basin, whatever. In this case, it's a reactor. It can be an existing or a non-existing system because the reactor doesn't have to exist, right? The first step you do is build a 3D geometry. So you construct a 3D geometry that is quite simple, actually. It doesn't need a lot of input to make. And then you include the relevant elements. What are the relevant elements? Inputs, inlets, outlets, aerations, aerator locations, mixers, if there are any, etc. These are the critical elements. Then we mesh it. So we divide this reactor in little cells. For example, if your reactor is, let's say, 1,000 cubic meters, and you have 1,000 cells, the average volume of one mesh cell is 1 cubic meter. That's how it conceptually works. And then finally, you get the nice colorful drawings. Most of you are probably familiar with. It's the output. The output can mean different things. It can be the most conventional output, a dead zone, velocity vectors. but it can be 3D concentrations of oxygen, ammonia. It can be particles. It can be sludge. It can be the gas holdup. It can be viscosity. It can be lots of things, actually. But we will not go into detail in this webinar because this will lead us too far. We have a lot of webinars and other content on our website if you're interested in. But this is the interesting thing when you look at CFD. When you have this output, you see things that are not optimal. In this case, you can see there's a red zone. Actually, this red zone indicates local high dissolved oxygen. It's all concentrated at one spot. You don't want it there. So you can do what-if scenarios while not having to actually do any modifications or tests with your real system. And then you can do, again, some simulations and visualize what's better. And finally, you find the optimal solutions or the final optimal designs that can be brought in practice. This is conceptually the core of the value CFD brings: testing flexibility and being able to really understand how you can properly design and operate your system. Let's make it very concrete and start with a very, very easy to understand example. This is a bioreactor, circular one, and we are putting in some pure oxygen aerators. In this case, they are Ventoxal units. They are from Air Liquide. And there are one pair actually, one here, and we will put them in. We put them in the system, and then it's a 1,500 cubic meters. They inject oxygen, and let's look at the velocities. I will pause it for a while. What you can see near the bottom, we are looking from the top. This is a slice. This is a 3D simulation, but we are looking near the bottom, and you can see a dark blue zone. This means sludge settling risk, bad mixing. So what we have done in this case, we have identified this, and this is how these what-if scenarios work. Let's move these aerators with 0.5 meter, rotate them 5 degrees, and look at the resulting design. And you can see actually with the same mixing energy that now your whole reactor is moving. Same mixing energy, no dead zones, by just slightly actually tweaking the angle of your equipment. So in this case, actually, the major gains was due to the small modifications in this specific case, an external recirculation loop and also a pump were saved. So there was sufficient mixing. It illustrates the value of CFD in this very simple example. More to come, of course, more to come. Let's go back a bit higher level and ask ourselves the question, where to apply CFD and who can benefit from it? We actually see 3 main phases. We have the technology development stage, the design stage, and when a system is built and operating, the optimization and retrofitting stage. Each of them have very different needs, but each of them can benefit from CFD. You can see the target beneficiaries or target groups that can most benefit from these domains. For example, it makes sense that technology development is most related to technology developers and vendors. While if you look at design of big systems, it is mostly the consulting and engineering firms that are working on it. Also, some utilities and industrial end users are directly doing it themselves. And then you have the optimization and retrofitting, which is mainly utilities and end users, but also to some extent, consulting and engineering firms. And the questions are different. You can see them on the screen. You can do a lot of simulations to actually answer questions on scale up in this phase or efficiency of the process, mixing in the other phases. Let's launch a small poll to talk about the target audience. We are a bit curious actually where you are coming from. And normally you should see on your screen right now a poll. So we ask yourself to indicate who do you work for actually? What is your target group? We are very interested in this because it has an impact on how we actually continue or where we put most highlights on in this webinar. So votes are coming in. We already have 36 votes, 40, it's going up. Perfect, almost 50 votes. Yeah, okay, I will end the polling. So I will just share the results with you. Normally you can see the results and it's a nice group of people here, but most of you are from consulting and engineering firms, which is nice to see. Many of you are end users, operating processes, and you have some technology vendors. We also expect some people from academia, yes, and there might be some some other people as well in this webinar. So thanks for your poll, for your input. Okay, so what is a successful CFD project? Well, we define successful CFD project as having 3 main properties. You have quality execution. So I mean, you trust the results and you can take very weighty decisions based on them. And you dare to because you trust them. On the other hand, you cannot wait for a year. So you also want some speed. So you want actually a person doing the CFD that can deliver the quality, but also the speed. Actually, you have to understand the process for that. But then that is still not sufficient because we have many customers with in-house CFD experts, and they are complaining that actually the in-house CFD experts are not available. So yeah, they cannot reach them because they are working on tons of other projects. So you also need the availability of the modelers. If you have these 3 combined, then you have a successful CFD project. What are common misconceptions? Huh? This is a nice comment we got on our Facebook channel of the company. We asked, what do you want to know about CFD? And one of the people asked, replied, well, you know, this person is really working, has a lot of experience in the water industry. I think he's joining because he said, count me in for the webinar. So I say hello by this, but he said that the ROI of CFD must be more clear and the access should be more easy in order to make it a standard mainstream application in the CFD, in the water world, right? In the water industry. So if we can demonstrate that it's more than just a fancy and colorful drawings, well, it should be a no-brainer. And this is really our goal. Yeah, we hear this from a lot of people. This is our goal to really address this in this webinar. A second question people have is it possible to simulate my system? What can CFD actually do? To address this, we will quickly show you a list which things are possible. It's not limitative, but you can do one phase, just water, mixtures of water and gas, water and solids. 3-phase, water, gas, solids. One example is an anaerobic granular sludge reactor. Another example is the backflushing of a sand filter. These are 3-phase systems. There are many others. You have special viscosities like anaerobic sludge. You have CFD coupled with kinetics, chemical or biochemical conversions. And you can have a scale from millimeters to milliliters to actually kilometers, which is this one, to millions of cubic meters. So we really want to stress that there is not really a limitation on the size and on the type of system you have. What is the time CFD takes? Well, full projects take 4 to 6 weeks on average in our company. But I must say it's not the simulation work mainly. Simulation work, talking with the team is mainly 1 week, like putting in the simulations, post-processing the data. Let's say 1 week out of these 4. But then the rest is discussion with your customer. You have to gather some data and things like that. But you can see that typically we are talking about weeks, not months. And for urgent projects, we finish them within 1 or 2 weeks if it's really, really needed. Time gains are significant in proportion to the time investment. That is really clear. Another very important one, and I'm happy to see that the majority of you is consulting and engineering firms. While outsourcing versus doing it in-house, a question we get a lot from our customers: what is the CFD strategy we should actually go or pursue in the future? Well, adequate CFD equals a full-time job. So we don't really believe you can do CFD properly. Properly means with the right level of confidence, so you can take weighty decisions if you're not doing it full-time. Still then, you can have a full-time CFD expert, but this person has no critical mass. Our co-founder, Usman Rehman, the CTO of our company, he said, going to a fluent forum is not sufficient. You need to be able to discuss with your colleagues. You need a critical mass because it's not easy, right? It's a specialist craft. And you need to have the relevant experience. If you're able to model HVAC systems, which is heating, ventilation, air conditioning, which is air simulation in buildings, for example, it doesn't equal that you're capable of really adequately modeling an aeration basin, which is a 2-phase process in a wastewater treatment plant. It is really key. We thought it was so important to put this on the slide. You can compare it to an IP lawyer. You want a lawyer, right? An IP lawyer doesn't equal an employment lawyer. I think everybody understands both are lawyers. They have similar backgrounds. They are using similar tools, but what they are doing or what they are capable of doing is very, very different. People really in the water industry need to understand this, because if not, you cannot really make the right decisions or judge what is proper quality. Well, let's do a small in-house ballpark. Huh? If you would decide your in-house team, for example, full-time CFD engineer, let's say in European situation, is 80K a year salary costs. If you want to manage that person and there's some overhead, 50K a year. You have some commercial software. We are not talking about open source software here. That's a separate discussion. We don't really get, well, believe you can really get there fast for practical applications. You combine it with some hardware, which is an amount, and in total, you exceed actually 100K, around 130,000 euros a year, if you want to have it in-house. Well, if we look at the projects and our big customers for us are customers that have multiple big projects a year. Well, this is a significant budget for outsourcing. Multiple big projects a year, actually, you can outsource. If you have an in-house expert, there are some other risks or things you should consider. Well, will the experts be available? Also take in mind, if you have in-house CFD expertise, that the management will not easily give you permission to outsource additional CFD to a specialist party, because CFD for many people means CFD. And it's very difficult to judge about the quality and the state of the art if there is just 1 or 2 or 3 people in your company doing it. So there is a lot of things about it. We are not judging too much here. Every situation is different, but these things are very important to realize. Final question, what is the cost and payback time for CFD? Well, typically in these 3 stages, it can vary a bit. You can see that the range is very widely. It depends on the project. You have entry projects that can be 5K, 8K. And then we have lots of projects that also go to 60K for a project. Maybe in the optimization retrofitting, it's a bit less. But apart from price, what is most important is the payback time. And typically we talk about a few months to 1 year of payback time, if done properly. But apart from the financial benefits, of course, you have better nights and more confidence. We were joking today, CFD is actually known also for colorful drawings or colors for directors. Well, we would like to add confidence for directors. This is so key if you build a big plant. 3 concrete examples from our customers. We could actually avoid for a drinking water company to install a large baffle. Not having the baffle there provided better mixing. It's a bit counterintuitive, but it led to cost saving 20K. Well, the cost of the project was less than 20K actually. Another example is saving a year of piloting. Well, the project actually paid back at least 3 times for this technology developer. These are savings of more than 100,000 euros if you're developing it or scaling up a technology. Then we have an operational plant, switching off 6 of the mixers of a large plant, led to a payback time of around, the energy savings only, of around 1.5 years. But actually the main benefit was improved effluent quality. And this was the main reason to set up the project actually. So these are like very, very concrete case examples, ballpark. So, well, now I will give the floor to my co-founder.
Wim, I'll just jump in. I think this is a question for you more, or Wisman can answer as well. But a question came in about the pitfalls of CFD. As we mentioned that professional CFD consultants are better to have the job done. Maybe just some input on that question.
Yeah, thanks, Celia. And thanks for the person asking this question. Yes, it comes again with the experience. Huh? If you have experience, you know the limitations of your tool very much. And with experience, we mean not having modeled like 3 plants. Huh? It's having modeled 20, 50, 100 plants. That is a lot of experience. If you know that, you're also very, very humble, in fact, when you have a new case on admitting that where the limitations of your model are. You dare to go further as well on the application side, but I would say a lot comes with experience. my colleague Usman, he will, I think he will definitely endorse that. So of course, no tool on earth is perfect. Every tool has limitations, but it's the expert using the tool that really has the responsibility of knowing the limitations and being open on it to the customers. Very, very important. Yeah, this is the reason for setting up such a company. You can really keep but accumulate and grow this critical mass of people. Okay, Usman, I give the floor to you so you can dig into the cases.
Yeah, thank you, Wim. Yeah, just to reflect back on the question, I think the experience plays a vital role. And also, I think a point you made earlier, Wim, was about you can, of course, CFD is a very generic tool. I mean, in its like true sense, CFD can be, if you have CFD knowledge, you can really apply it on a wide variety of applications. But I think when we talk about the experience really means a relevant experience into certain technologies or certain processes. I think that makes much more makes your experience much more valuable. And I think that's I think a very important and very interesting fact about the CFD modeling. That the more relevant experience you gain, the higher confidence you also get into certain decisions in modeling terms. So I will not spend more time on that. So what are we going to speak about here is different showcases or different case examples, which are actually connected to different stages, what Wim mentioned. So first one is the technology development. So we just gathered few cases. For example, for the technology vendors, I think there are a few things which they are very interested into, or which are very, very useful for typical technology vendors. And the most important one is that how you can accelerate your technology development. So it means that CFD can really minimize the time to market. It can significantly reduce the costs which are related to your piloting or your experiments or your technology development. And then it also gives you a huge testing flexibility, which means that you can do all type of configuration testing, different operational testing, like what-if scenarios to really increase the application of your technology. On top of that, in the meantime, it also provides a lot of insights, which are normally sometimes not possible with experiments or with just measurements. So overall, I think there are a lot of benefits for technology vendors. It saves you cost, time, and also leads to more reliable process performance and additionally confidence and a new insight. So I will start with one example. So this is, in this case, the client, it's a Japanese client who were modeling, who were actually constructing a pilot for MBR bioreactor. And they had a very small lab scale bioreactor, which they wanted to scale up to a demonstration scale. So almost 30 times more than their lab scale. So this is a huge transition. It involves a lot of expenditure. If you have to do it stepwise or have to just build it and then start retrofitting or start optimizing the design. So what we did in the CFD was that we started with a lab scale, validated the CFD model, then we moved to the large scale, and then we tested several configurations to come up with a very good design which will optimally perform. So this design, this CFD modeling actually helped them in saving a lot of time, and there was a drastic reduction in time to market for this technology. In this case, we tested different designs and like around 5 designs in 5 weeks. So this is the order of magnitude we were working in this case. Okay. So this was the final design which was working the best for the client. In this example, this is a prototype of a tubular membrane. In this case, it was very interesting because client already already found out that there is a certain design of the tubular membranes which is working. But what they didn't know why it was really working. So for that reason, we performed CFD simulations and actually figured out that the helical ridges, so these are like very small tubes, like of 4 or 5 millimeter. So helical ridges inside these membranes can really increase the shear stress, which means that it can clean the membranes inside very fast, and it will increase the performance of the membrane. So we can see it on these curve, Riemann open curves for the shear stress, that the red curve, which is for the helix case, is on the right, which means more shear compared to the plane case, for example. So this was a very interesting study. In this case, we had 3 designs which were tested in 2 weeks, more or less. Okay. So this is another example. It's a novel electrochemical technology. In this case, the idea is that we fluidize the particles using using water. And as you can see that the particles which are sitting at the bottom of a reactor, and if you are pumping some water from the bottom, it will be probably very hard to fluidize them on upfront. So we started using the CFD modeling for that, and we figured out that if we just go by the general engineering design, we found out that the particles were not really suspending, so they were just falling, as you can see it here. So we tried to make some more changes by adding some design changes, which means, for example, moving the liquid inlet from upwards to downwards, and see if it can help. We went on to make this cleaning, and eventually we got the particles to suspend. But as you can see, that these fluidization of the particles was not very uniform. It was very fast, and every particle was like really going to the top, probably leaving the reactor in relative well. So we further optimized the design, and then you can see now the fluidization of the particle is much more uniform. They are also coming back, and they will keep fluidizing. So this is a very good example where we started from a very basic idea, and then we implemented the whole. So the whole design was really developed in the CFD. In this case, we tested around 6 designs, and it took us around 4 weeks. So in this case, really CFD had been designing. Okay, so the next stage is normally the where the more engineering firms are interested, which is about the design of the large scales or the design of the real scale facilities. In this case, I think CFD can really support the engineering practices. It can really support the design decisions which based on normal engineering practices the designers make. So CFD can really confirm some assumptions and confirm some hypotheses, and can really give you confidence in your design decisions. And it becomes even more important if you have some risky processes where you are limited with respect to space, for example, or in general footprint of the technology. It also provides you, I think, with the competitive edge, and eventually the end user becomes much happier. And then I think for the engineering firms, it's also good to have a reliable CFD party, which can provide you much more better project understanding. So I think, again, for all the benefits are there for the engineering firms in this aspect. So I will show you some examples in which I think we were able to help the firms. So this is an example of a very large water storage basin. So in this case, the volume of this basin is around 4 million cubic meters. And the question here was, shall we use the aeration or not for better mixing of the water, to have a good mixing of a good quality of the water? And we tried to do it at several different flow rates. And this we tested 4 designs. It took like 4 weeks. And we figured out that actually, if you place your aerators in very strategic locations, you can use much less energy to get the very optimal mixing. So in this case, it actually significant capex and opex were saved, and also still having a very good mixing in the large basins. Another example is actually an A-stage technology. This is a new technology, and you can see on the video. There are 2 reactors which are alternatively working. So one is aerating, the other one is settling. And in this case, you can see, for example, we just modeled this reactor, and there is this outlet pipe which you see here. And the idea and the question here is how we can better design our infrastructure so that you have enough fluidization in the reactor. So infrastructure was something which we modeled. In this case, we designed 4 different designs, and it took around 2 weeks. So if you look at the results, so this is where the engineering, so this is where what was suggested by the engineering tools for engineering practices. But you see there's a little region in the reactor which is kind of suboptimal. So it's not getting enough flow. So this is how, so by testing different designs, different configurations, eventually actually very little pipe modification, we were able to actually have a very good mixing in the whole reactor. So this shows you that how actually CFD can complement your engineering practices. So this was a very powerful and useful example.
Usman, if I can just jump in.
Yeah.
A question came in about the MBR example. If our models are coupled with ASM like wastewater treatment models, maybe that's a good one to answer now. Or
yeah, indeed they are. So in this typical example, actually we were able to actually brought more confidence for the end user because the more accurate. Sorry, I will just try to get it to the. Yeah, actually what the graph you see here is actually ammonia. And this is by integrating CFD with the kinetics, so ASM1 model. So this was really integrated here. And why we saw it, because it was very crucial for the client to really see the water quality at end. So indeed, so this is an advanced model where we integrated kinetics with CFD to really look at the water quality, treated water quality. Is that the question, Celia, or?
Yes.
Yeah, I can add something to that, Usman.
Yeah.
So so what many people are familiar with is like velocity fields, and mixing, generally using CFD for mixing. You can have a dead zone or bad mixing or poor mixing or suboptimal mixing. But in the end, what you are really interested in as a process technologist or a process engineer is the impact of that dead zone on your process performance. And by actually integrating directly the kinetics in CFD, which we actually do on a routine basis, I think we have done it for really many customers. You can go a step further in the optimization, because it's not always that straightforward. What is bad mixing or poor mixing or good mixing? It depends on your process. Yeah.
Yeah. And in cases, for example, with large basins where you don't have actually you don't really need kinetics, there we do virtual tracer testing, for example, to just quantify the mixing. So just looking at the vectors or the velocity fields, sometimes it's not sufficient. You cannot draw very strong conclusions. So by just adding this extra layer of complexity, well, I will not call it complexity, but extra advanced modeling, you can actually see mixing really quantified. Okay, I will try to get back to where I was. Yeah, so here is the example of a sand filter. So sand filters during the filtration, they are capturing the pollutants on the top, and then there is backwashing to get rid of the pollution from the top. So the backwashing is complex because you have water, you have air, and you also have, of course, sand. The problem with that is that if you don't have homogeneous backwashing, you might either wash out your sand, or either you don't wash out your pollutants, which are like normally in the sand during the first stage. So in this case, we modeled the backwashing to just see how the fluidization of the sand is happening. I will just run the animation. You see, this is the sand fraction, which is being fluidized first with the water, and then at some point air will turn on and you would see much faster the fluidization. So in this case, we were comparing two different designs and looking at the inlet location, what is the better position of the inlet, such that you get the best of the performance of the sand filters. We tried different designs, like 4 designs in 4 weeks, and eventually we were able to figure out the best possible configuration for the sand filter for different structures. The last stage, which is more for the end users, for the utilities, optimization and retrofitting on large scales. So I have a couple of examples for that. Normally, for the end user, it's important that they are not overspending energy. Of course, they want as much as efficient with energy use, and they also want to, of course, reduce as much as possible OPEX and CAPEX. And on top of that, they also want that their process performance is always optimal, and there is no problem at that end. So I think, again, they can benefit from all these different options if you're using CFD. The first example is of a homogenization tank, where the client was really looking at the sludge mixing and was trying to avoid struvite accumulation in the tank. Struvite happens to be like very fine particles, which can accumulate and then probably will give you headaches when you are going for the sewage treatment later on. So they had a tank, but it was causing problems with the accumulation of struvite. So one solution was to just have better mixing by installing extra propellers. So initially, the plan was that they had 2 propellers on the side so that they can keep this whole tank in motion, so the liquid is completely revolving. But then we figured out that this is not enough, and you need a central mixer which can somehow provide you this vertical flow, so there's enough suspension of the particles. We tested several designs, for example, 6 designs in 6 weeks. And then we found out, if you look at these 2 figures, on the right side, you have actually 3 impellers. So 2 side impellers, 1 in the middle, in this case as well. The only difference from right to the left figure is the angle of the outer impellers. So the moment you make or turn the impellers in such a way that they start synergizing together. So the central impeller and the flow caused by the outer impellers is synergizing with each other. So they are not like counter-flowing against each other. So in the right example, there was a counter effect, and the right and the left, they are more in synergy with each other. You can see it actually in the next slide. Here I will just run the animation for 3 different cases. So this was a case when you just had the outer impellers. In this case, we already had the central impeller, but the angles were not optimal. And in third case, in scenario 2, you have the angles very optimal. So you will see the particles. So these are all particles which are actually fluidizing. In this case, they don't leave the central part. They are all accumulated here. So this is the current situation. By implementing some side impellers, you were able to move them, but they were still kind of caught up in this region where you had this flow against each other. But in this case, once everything is in synergy, you can see that the particles are completely in motion and are very good suspended. So this was a very interesting project where client was already going to implement. So in this case, we decided the impeller type, positioning, and of course also the specifications of the impellers. Another example is I have to go back. Yeah, so this is an example of a secondary settler, and the client was actually looking at increasing the capacity of the settlers by adding some extra retrofitting inside the settler, so that they can still have very good settling without compromising the effluent quality. So without having much more TSS in the effluent. First thing which we found out in this simulation was that it's very important that we do a 3D simulation of the settlers, which is conventionally not the case, because conventionally the CFD modeling of the settlers is mostly in 2D, which gives you some indication. But if you are going to test some features or some design features in the settler which are inherently 3D, 2D simulations cannot take that into account. So this is important, that if you're going to check, for example, certain baffles, certain walls, certain withdrawal systems, you have to be sure that your system is adequately designed inside the CFD to take into account all these details. So in this case, we tested 8 different designs, and it took us around 10 weeks. And we were able to actually also validate this, because this was a special type of sludge. So which was where PAC dosing was happening, so sludge was like very good settleable. So we tried to validate this with our model, and we found that it was the CFD simulations or results were very much in line with the measurements. And then we tested different design scenarios, and we found out that scenario 1 was better than the scenario 5. So this was a very good finding, because scenario 5 apparently was the most expensive option for the clients. They were actually, because of the CFD, were able to choose, they were going to invest anyway, but then across different options, there was one option which was the most expensive, which was, in their opinion, going to be the solution. But eventually CFD simulation showed that this was not really the right approach. Rather, a cheaper was a much better performing option. So definitely CapEx was saved in this situation. Okay, so that's it.
Maybe I'll make use of the opportunity to jump in again. Yeah. A question came in about the fouling mechanism on membranes. If that is taken into account in the modeling. For example, the fouling mechanism due to oil adsorption.
Well, not really, not explicitly. The case I showed, the tubular membranes, for example, in that case, no, it wasn't taken into account. But the common consensus is the higher the shear, the higher the cleaning of the membrane. So that is something which you can correlate with your process.
Okay, thank you.
Okay, good. We can go to the conclusion section. Yeah, if there are any more questions, it's now the moment because we have some time left, and after the conclusions to go a bit deeper on the questions. Huh? So feel free to ask any questions you have on the cases or on the stuff we have presented. Good. Conclusions. Well, as you have actually probably seen, we only could select a few cases, but there are so many nice projects, nice different technologies, different applications we could not show, but have been working on. Actually, you can assume that CFD can be used to model almost any treatment process. It can be physical, chemical, electrochemical, biological, but also other systems, the more conventional ones, flow distributions, storage systems, they can all be readily modeled. The thing is, it's not it's not embedded sufficiently yet in the water industry. And this is one of the reasons we are setting up such webinars to really spread this message on what's available and what's possible. Each group has different needs and benefits. So all of these three utilities, or chemical companies, for example, or consulting and engineering firms, or technology developers and vendors, they are all customers of us. The projects look very different. They are all CFD projects, but they all look very different. The speed, time restrictions, the time expectations can be very much different. The in-depthness can be very much different. The number of cases, the size of the project, the approach you have to take. So all of these things are very important in projects, and we really try to tailor our way of working to these target groups. So this is quite important to understand. Often this resolution is not really present in many people in the industry. And well, we have seen so many times, I mean, I think our company has now finished around 150 projects, full-scale, pilot-scale projects. The benefits of proper application of CFD are really significant and vast. So these ROIs, these payback times we have shown are really not really exaggerated. If it's really appropriately applied with the right level of expertise and experience, you can really do a lot with it. And again, it comes down to these needs of utilities, the engineering firms, and the technology developers and vendors. So I hope these key messages were really clear. Now, we didn't dig very deep in the cases in this webinar. There is a lot of information available on our website. We are publishing a lot of papers, writing a lot of blog abstracts, and we also plan to do some more. And in regular times, we present a lot of this information at events as well. So if you want really much more information on a specific case, you can always contact us, right? That's very important. So we can continue with the Q&A. There are questions coming in, but before that, for people that are really like time restricted or would like to leave, but we still have 10 minutes left. Well, don't forget to fill in the survey, the questionnaire after this webinar, but we hope that you stay a bit with us still for the questions. So, also, if you really want to have our latest updates, cases, blog posts, webinars, you can actually scan this QR code. And the best way is to follow us on LinkedIn. That's really powerful. Okay, I will go back to Celia. Celia, do you have some additional questions?
Yeah, actually quite a few questions came in, or maybe I'll follow them chronologically. One of the first that came in was of all the examples we showed, we need a good geometry and mesh, and how we cope with this, because we are delivered quite quickly. what tools do we use, and do we have people focused on geometry and meshing? Maybe you or Usman can answer this question briefly.
Yeah, Usman, are you able to answer this question?
Yes. Yeah. Indeed, I think for the geometry mesh, one thing is that the more you do it, the better you get it. But we definitely have some exclusive people who have gathered a lot of experience in creating geometry and meshing. So we have made the whole process much more automated, much more less and less manual. And also we have, I think, company-wide or our in-house in-house tips and tricks which we use to really quicken the whole process.
Yeah, maybe Usman, now that you're there, another question for you in case of activated sludge systems, how we take into account different sludge types, specific microbial activities, presence of filaments.
Yeah, so it depends on your final objective. So if you're really looking at a really micro level, of course, then you need to take into account a very detailed sludge rheology. But if you're looking at the macro level, I mean, how the mixing is happening in your bioreactor or in whatever system you are working on, you have models for defining, for example, bulk density of the sludge and the water mixtures. You have, for example, rheology models which you can just take into account for better depiction of the sludge flow. But then, yeah, I think largely because we are dealing with really the real life cases, not really in depth microbial flows, for example. So I don't think that we really need to dig too deep. But we certainly use rheological models for viscosity and density to take into account different types of sludge.
Okay.
For example, it can vary based on TSS. So if you are modeling a sludge which is in the secondary settler, it will definitely reflect in the rheology of the liquid or the fluid which you're using in the CFD. Or if it's in the bioreactor, you would have different MLSS concentrations, and then eventually your rheology will be different. But this is taken into account.
Mm-hmm, mm-hmm, mm-hmm. Yeah, then an interesting question. I don't know if you want to answer or Wim, but if there have already been commercial attempts to use CFD to build and calibrate less computational intensive linear models for real-time and predictive use. I think maybe an important factor there is that computational power now is no longer really an issue, or there are solutions, or what do you think?
Yeah, shall I answer, Wim? Yeah, well, what we found that if we don't use CFD, we are normally there are flow sheet tools, for example, to calibrate your predictive power, for example, of the model. What CFD does, it takes into account all the details of the flow dynamics, which partially are accounted in the calibration. So we at least take that uncertainty out by performing CFD kinetic modeling. So I'm just taking out that example. It can be generally applied to anything. But what we still do, there's another step, which is actually simplifying the CFD model into much more simpler modeling, which is called compartmental modeling. So it's a network of flow sheet tools, actually. And then in that case, you can perform dynamic simulations. You can calibrate to your certain process, for example, if I've understood the question correctly.
Yeah, indeed. Like the question was about real-time usage, huh? And
Yep.
yeah, for the real CFD, we are not yet there for real-time uses. But indeed, like what Usman was saying, what we are using often is compartmental modeling. We have a recent paper on that. Even if you are interested in, we can send it to you how the methodology works. Yeah, one example is these big basins. Usman has shown these large ones of millions of cubic meters. One of our customers asked us the question, hey, in the future, we see more and more droughts coming because we already see the impact of climate change. It was a case in the Netherlands. So we have quite a decent annual rainfall, but more droughts. More droughts means including salinity, well, increasing salinity in surface waters. And they wanted us to actually dynamically predict, hey, if a chloride peak comes into the basin, basins with a residence time of 60, 100 days, how long do we have to actually take the necessary actions in the downstream water treatment plant? Well, you cannot actually handle such a system with CFD because, for example, you will not model a 5 years time series of chlorides with CFD. But on the other hand, you also cannot assume the whole basin to be completely mixed. We have shown so many times that these basins are not completely mixed. So what we then do is we build a compartmental model, we define these mixing zones, and these models are actually able, well, they have the ability to be used in real time, but they also combine the properties of CFD, not assuming the ideal mixing. There's a lot of potential in there, also in biological wastewater treatment modeling, chemical models, to actually improve the models themselves. Because often we see people, this is a bit more technical, but often people that use kinetics, they have to tweak some of the kinetic parameters to include or make up for some of the hydrodynamic factors that are not in the model. And this is what compartmental modeling is solving. If you look at digital twin applications, the real-time digital twin applications, if we look at that, for example, within 5 years, you need very accurate models. If you want to, for example, partially control a plant based on the model, and then these tools can definitely help.
Okay, some more questions came in, maybe also an important one, if our models need calibration.
Yeah, so Usman, you or me?
Yeah, I can do it. So, so CFD inherently, we don't do calibration unless you have a very good experimental measurement data, which is very hard to collect. I mean, if you're going to really calibrate your turbulence model, you really need very good data. And normally at such large scales, you don't have that. So we really don't do CFD calibration. So there's no calibration in the modeling of CFD.
Yeah, maybe I can add to that. As we have talked about before, we do a lot of coupling of kinetics with CFD to solve specific issues. Many examples can be found in the scaling up of technologies. In those cases, of course, you have kinetics involved. Kinetics are dependent on your water matrix. If it's a chemical or biological process, they are dependent on your specific water matrix. Of course, then we use the conventional methodologies, batch testing, or they have pilot data, or they have full-scale data to calibrate the kinetic part. But we separate the kinetics from the hydrodynamics. And indeed, we try to do the hydrodynamic modeling properly as such that we don't have to calibrate it, because that's very difficult to know where you will end up then. We try to, like, instead of calibrating the CFD model, make them more realistic based on experience.
I hope that answers the question. Another one that came in was about digesters. And I think that's a very interesting one, that the feed can be very variable. And for example, also temperature, and how we work with these variable input parameters at the inlet in order to, for example, guarantee a good mixing within the digester.
Yeah. Yeah, so yeah, I will start maybe, Usman, and then you can complement me if you have to add something. Yeah? But yes, digesters is, we call it, we joke sometimes about it. We joke about a lot of things, but yeah, digesters is literally a black box, literally. Well, not many people know what's really happening inside. And yes, you have activated sludge digesters. It is completely different than a food waste digester or a manure digester. Like rheology-wise, solids-wise, they are completely different. So yes, indeed, you have to more or less account for these things based on literature data and experience. Now, what is one very important thing there is some sensitivity checks. For example, do we need the accurate, like detailed rheology data of that specific digester? I wouldn't say not really. Let us be practical. If it's a design project and let's say make a estimated guess based on experience, and then still you can do a sensitivity check. Okay, let's change the viscosity, the rheology a bit, and let's see within which domains our conclusions still hold. And what we see most often is if you then start comparing designs, for example, you shift to a completely different impeller type, or you feed differently, well, that the comparison between these scenarios is very, very powerful. Even if you don't have like 100% of viscosity captured, but more or less have it captured. Temperature can be included. We have had a couple of projects on that. Temperature is an extra equation you switch on. And for some customers, it is important. For example, in the more warm areas where you have a temperature, a day temperature of 40 degrees, right? With a very hard sun on the surface of the digester. In some cases, for example, temperature from outside is even important, not only the temperature gradients by the production. So a lot of these things can be included. Again, it comes down to the objective. This is where we always start with our customers. What is it exactly what you would like to achieve that you currently cannot achieve without CFD? If we can crystal clear define that, we can come up with the right methodology. That is really an important one. I don't know, Usman, if you have something to add to that question.
Oh, that's perfect.
Okay, I'll ask another question then. Yeah, one small question I think now for you, Usman, is what we use for rendering. It's a bit more in details, and then also your thoughts and experiences on modeling oil, water, gas systems, considering the capabilities to include pressure systems. Yeah.
Well, first question, rendering. There are a variety of tools available for rendering. There are also commercial tools which come together with the solver. In that case, it's mainly ANSYS we use, and also the post-processing tools which come with ANSYS. But there are actually a lot of tools available for post-processing, so for rendering or for anything you can use. Whereas the next question about oil, water, gas systems, definitely this is something which just relates to different rheology. If you have to take into account oils in your system, or you have to take into account gas in your systems. As I showed, there are some examples where you have different combinations of different phases. So it boils down to the fact that if you know about the process, you can actually integrate whatever phase there is into your model. We haven't really given any example of oil in the wastewater water. It's not really relevant, but I suppose it's very, very similar. But again, I say that, as we also said, that you need to have the background knowledge about the process itself to model it. So it's not about the question of if we can model. I think most of the CFD people will be able to model an oil gas problem, but I think it's important that they have the right background knowledge.
Okay, thank you. I think there's one question left that came in the chat. How is this different from hydrodynamic modeling used for modeling thermal effluent plumes?
Can you say again, Celia? I didn't really get it.
How CFD, I assume, is different from hydrodynamic modeling used for modeling thermal effluent plumes.
Thermal effluent plumes. Well, the only thing I can say is we had a specific case on that, Usman. I mean, with the discharge of this effluent in the canal.
Yeah.
That was for us at that scale. It was not really different, but it depends on the scale of your system. But in that case, we captured like almost 1 kilometer stretch of a river, and we could like nicely, calculate the thermal spread and the local temperature gradients in that system. Yeah, it's feasible. Huh? Yeah.
I think
likely we have to close here, I think.
Yeah, I was going to say the same. We have answered the questions, and I think we went over time 5 minutes, so we can round up. If other questions arise, anyway, we are available and you can contact us. So I'll let you close, Wim.
Okay, perfect. Thank you, Celia. So thanks, everyone. I want to thank you again for the persistence, because you are really the diehards staying until the last bit. thanks for joining. It was a pleasure, talking to you. And we would really appreciate if you could share your feedback with us using the feedback form. We will also do a mailing after this webinar. So please send us your questions and share your feedback. And we really hope to see you again in the next webinars. Thanks a lot.
Yeah, thank you so much. Bye-bye.